test. Okay. Hello, everybody. I'm Benma. I work on the Bitbox hardware wallet. And recently, I've been working on integrating a new protocol for Bitcoin, which is called silent payments. And I learned a thing or two about it. And I want to teach you some stuff I learned about this very interesting topic, in my opinion. All right. This talk will have two parts. One is just a very technical deep dive into what silent payments are. I'll try to keep like a mid-level, so it's like easy to understand, but still you can understand how it works in detail. And then the second part is how it integrates with hardware wallets. And this is kind of special because it changes the role of what a hardware wallet actually is. So spoiler, it's not a signer anymore only, but also a transaction generator. All right, let's get started. So what is silent payment? It's a new Bitcoin address format. And it's a protocol for static addresses, which prevent address reuse. That sounds kind of like a paradox, but we'll resolve that paradox shortly. So it removes the need to manage multiple addresses while still preserving privacy. So the authors of the proposal are Josie Bake and Ruben Sampson. They made like a pull request to the Bitcoin improvement proposals GitHub repository, where they like kind of specify the whole protocol. And you can see like it received an impressive amount of reviewers from the community, from the Bitcoin developer community. Like on the side, you can see like a list of reviewers. If you follow Bitcoin development, you can recognize a lot of the names there. And I'm also happy that my own name is like present there. It's Benma, somewhere in the middle. Like I also reviewed a small portion of it related to hardware wallet integration. And so what's the problem it's trying to solve? It's privacy loss because of address reuse. Let's look at a simple example. Right, you have a cool project, you want to collect donations, you put your address on the website, and then the money flows, hopefully. But of course, the problem is, if you have only one address on your website, anyone can go to the block explorer, paste the address, and they can see all the transactions that came to the address. They can see how many donations you collected, and maybe in the worst case, they can even see what you used the money for. Well, or maybe in the best case, who knows? Sometimes privacy is not so bad, right? And then if you want to avoid address reuse to just have more privacy, then people have to generally find a way to give you a new address every time you want to make a transaction. So it's interactive. And on the website, it means you have to operate a server with maybe BTC Pay server, something more complicated to set up. And this is a lot harder than just making a web page that is static and you just paste your address inside. And there's other examples. For example, if you have an exchange deposit address and you want to have no address reuse, you have to log in every time, make a new address, register it, make sure it's correct, and so on. It's a very complicated UX. And so silent payments aim to solve this problem by just having one static address. But yet, when you make transactions, it will always be generating a new address, like on the fly. All right, before we go into this, just a refresher about how transactions work today in Bitcoin. So every transaction, let's say Alice pays to Bob. Alice is on the left side and Bob is on the right side. You have inputs to the transaction and outputs. Normally you have like an output that goes to the recipient, like Bob, and then some change back. And every time you make an output, it creates a UTXO. It's called an unspent transaction output. This is like a new coin that you can generate. And on the other side, if you have coins that you received like this, you can spend them by feeding them into a transaction. And this kind of destroys the UTXO again. All right. So now, if you look at the output, what is actually inside an output? Usually, it's a public key inside the output. So a payment output is locked with a public key. And you can spend it again with a private key, right? And if you have an address, like Bob gives you an address to make a payment, then this address just encodes the public key, just includes it. So the output will contain this public key. So whenever Bob wants to spend it, he just needs to use his private key. All right. And in silent payments, this changes a bit. It's not just a public key. Well, it is a public key in the end, but the output is generated from scratch for every transaction based on some cryptographic techniques that I want to go into. And the address is not like before, like a BC1 something address. It's the new address format. It starts with SP1 and goes on. Just a quick look at the silent payment address. It's a fair bit longer than a normal address. And it's because it doesn't only contain one public key, but two public keys. It's called a scan public key and a spend public key. Okay. So to understand how silent payments work under the hood, we cannot get around looking at cryptography, how it works in Bitcoin, like private public key cryptography. So I'll just make a quick introduction to this, just enough so we can understand the rest. Right. So what is a private key? Private key is basically just a very large number that no one can guess. Maybe you've heard of this before. And for each private key, there's a public key. And then what are public keys? For this talk, it doesn't really matter so much what they actually are. They are points on an elliptic curve. It's called elliptic curve cryptography. But it's just basically elements that you can add together. And as a fun fact, you can actually forget this again, but I always think it's interesting to look at what it is. It's like public keys in Bitcoin are basically points on an elliptic curve, and addition is defined in a special way. It's basically you have 2 points, and to add them, you draw a straight line through them, you find the intersection with the elliptic curve, and then you mirror it on the other side. And that's a very strange way to define addition, but it turns out when you do this, you kind of get the same structure mathematically speaking, like just normal numbers. Like for the rest of this talk, you can just always assume they're like just normal numbers. For example, 2, 3, -1, etc. Because you can add them together, right? So you can do a multiplication. 2 times the public key is just the public key plus the public key, and 3 times the public key is also public key plus public key plus public key, and so on. And like the high school mathematics, that like all those like arithmetic laws and so on, they are the same like with numbers. You can just pretend they are normal numbers. For example, it doesn't matter if you will do 1 plus 2 plus 3 or 1 plus 2 plus 3. It doesn't matter which order you add stuff up. It's always the same result. And also the distributive law, it's for example 2 plus 3 times 5, right? That's 5 times time. 5 times 5 is 25. It's the same as if you do it like piece by piece. Like 2 times 5 is 10, plus 3 times 5 is 15. You add them up, it's 25 again, right? So this example below, you have 2 times 3 times the point, and you just like expand it, and you have 5 times the point. All right, this is one ingredient for silent payments, just like the basic arithmetics. And the so what is how does the public key correspond to a private key? Right, so you can pick any arbitrary public key that is on like in the curve, and you call it the generator. It doesn't matter really which one it is, it's just important that everyone agrees on the same one. And it's called a generator because if you add this one to it, like if you multiply this by a number, this is how you get your public key. Like for example, if your private key was 2, your public key is just the generator times 2. And if your public key was 3, the private key was 3, it's the generator times 3. And of course, in practice, your private key is very, very large, right? Okay. And it turns out that if you do this multiplication, you can do this very quickly. You can very easily go from private key to public key, but the other way is very difficult. There's like, no one knows how to do this, except if you have quantum computer, of course, right? And this is called the discrete logarithm problem. Maybe you've heard of that. Okay, this is ingredient number 1 for silent payments. Ingredient number 2 is elliptic curve Diffie-Hellman. So what is that? So imagine you have Alice and Bob. They each have a key pair, like Alice has a public key and a private key, and Bob has also a private key and a public key. They can both make a computation to get a secret that is the same for both of them, but they only know each other's public keys. It's pretty amazing. So the shared secret, if Alice wants to compute it, she just computes it by multiplying her private key times Bob's public key. And if Bob wants to compute it, it's his private key times Alice's public key. And this value ends up being the same. And we can look at why. So this is where we do the arithmetics I was telling you about before. So if Alice computes it, it's 8 times like her private key times Bob's public key. We can just replace this part, right? Then it's 8 times B times G, like her private key times his private key times the generator. And you can just drop the parentheses because of the associative law. And then you have 8 times P times G, right? And the same you can do for Bob. Bob computes it as his private key times her public key. insert this, and you drop the parentheses, and you have the same result as you can see. In both cases, it's A times B times the generator. So now you have like two very important ingredients. You have like just private and public keys, and you have a way to compute a shared secret between the sender and the recipient. All right, so time to build the silent payments. So ingredients, all the key pairs. Alice has one, and Bob has two, like the scan key and the spend key from his address. And then Alice, when she wants to pay Bob, she can compute the shared secret as her private key times Bob's scanned public key. Okay. So as an overview, Alice wants to pay Bob, right? Alice gets the public keys of Bob from the address, right? She gets it from the donation page, or he sends it to her via Telegram or something. She can get the public keys from there. And when I mean her, I mean like her wallet, right? She uses some wallet. And then she also has a key pair, but what is a key pair? Like, there's no address that Alice makes and sends to Bob. It's not an interactive protocol like this. And it's a pretty elegant part of the silent payments protocol in that the keys from Alice are basically already in the transaction inside. Like when she spends her own coins, each of the coins is already locked with a public key, right? Because she also received coins. And when she spends them, she uses her private key. So if she has private keys and public keys in the transactions, she can sum them all up, and she gets a combined private key. Like the individual private keys are just numbers, you can just sum them. And the public keys behave like numbers, you can sum them too. And it turns out that the sum of the private keys is the private key of the sum of the public keys. So you have just a new key pair, like one key pair for Alice for the whole transaction. And so at the bottom, there's like a quick derivation about how you do, like how you can verify that it's true. But don't have to really go into this in detail. Okay, so back to the overview. So what is the goal here? Alice wants to pay Bob, so she wants to put the public key into the payment output for Bob. But what is the public key that she wants to use? In traditional payments, it's just going to be straight the public key from the address that Bob gives her. And now we'll just do a few attempts, like a few failed wrong attempts to see what we could do to try, and then see why it doesn't work, and then build up towards the final protocol. All right, so what if Alice just used the shared secret as the public key for Bob? She just locks the output with this public key. Right, shared secret is her private key times his scanned public key. So what would be, like, any guesses? Anyone has a guess who can spend the coin that is locked with this public key? Let's take a look. So you can replace the scan public key with what it is. It's the private scan key times the generator, right? Then you can drop the parentheses again, because the associative law. And then you can see that the private key of this shared public key is A times B, which means if you actually lock the coin like this, then both of them had together like multiply their private keys to be able to spend the coin again. But this is not what we want, right? We want only Bob to be able to spend. So here's another attempt. There's a trick, it's called hashing. So a hash is basically a function that you can feed any data, and out comes a number. So it's kind of a trick to convert the shared secret into another new private key. And we could then lock Bob's output with this new public key, based on this new private key that is the hash of the shared secret. And what's the private key here? It's the hash of the shared secret. But both Alice and Bob can compute the shared secret, right? So either one of them could spend the coin. So this is also not what we want. We want only Bob to be able to spend. Yeah? Yeah, I'll quickly go back. This is here. Right, so both have a key pair. And at the bottom you can see the shared secret is she uses her private key, which she has, of course, and his public key, which is public. And he does the same in the opposite order, but it ends up being the same value. Okay. So at this stage, we have like this public key that the private key is the hash of the shared secret, so both could spend it. And here is where we actually use the second public key that is in the address of the silent payment, which is the spend public key. And if we just add it to the whole thing, then we make it so that only Bob can spend it again. So we can verify this. So what is the private key of this output's public key? Right, so we can again replace the spend public key, which is the private key times the generator. And then we can factor out the G, right, the generator, like this. And you can see the private key is the hash of the shared secret plus the spend key. And the spend key, the private spend key, is what makes it so that only Bob can spend it again, because he only knows his private key. And this is basically how you make a silent payment in a nutshell, like, or what the wallets will do. So as an overview, right? Alice wants to pay Bob, so he creates an address with 2 public keys inside and gives them to Alice. Alice then locks the coins with this public key, which is the spend public key of Bob plus the hash of the shared secret times the generator. And the shared secret she can compute with her private key and his scanned public key. And then when Bob gets the money, he can spend it again with the private key. That is what we just looked at in the previous slide. All right, so integration into hardware wallets. So this is kind of interesting, because if you want to have support for sending to silent payment addresses in the hardware wallet, then it means that the hardware wallet is now something different than it was before. Before, in normal transactions, like the app, for example, the Bitbox app would just make the transaction and send it to the hardware wallet, and the hardware wallet would sign it, you confirm it and sign it, the signatures go back, and you send, that's it. But now with silent payments, the hardware wallet has to not only sign, but it also has to actually generate this output, the silent payment output for Bob. And this is because only the hardware wallet has the private keys, right? And the private keys needed to compute the shared secret. And the shared secret is needed in this public key. And the trouble here is, it introduces some new risks, right? For example, the hardware wallet is just a machine, right? But it could have faulty memory, for example, or it could have implementation bugs. So you could imagine you like have this hardware wallet computing this output, but maybe along the way there's just a memory issue, like a bit flip, something goes wrong, and then you have an output that you send to the host again, to the wallet, and you send the money, but the money cannot be spent by anyone ever again, because it's just the wrong output. Like no one knows the private key of this one. And some people also worry that the hardware wallet itself maybe could be malicious. It could be that people working on the hardware wallet could just make a fake output that sends the money to the developer, for example. So when I was working on this a few months ago, I put out a tweet about this, because I was working on it, and then I realized, oh, wait a second, this is actually a big problem. Like I cannot actually deploy this if you have no solution. I wrote this like thread about the pitfall with silent payments and hardware wallets. And I write like, if a bit flip were to happen in the generated output, the bitcoins would be sent to nowhere and lost forever. Or at least until this discrete logarithm problem is solved with quantum computers or whatever. Because you need to just undo this. And to make things worse, the host wallet, like the Bitbox app, it cannot perform a sanity check, as it would need the private keys of the signer or the scan key of the recipient to verify the output. And it's always good to just make statements that are wrong on the internet, because someone will come and correct immediately, right? So this luckily turned out to be wrong, and the authors of the BIP came, like Josie Bake and Ruben Samson, and immediately corrected me. And basically taught me a way where you can still verify the correctness of the computation. So let's look at the flow of the hardware wallet and the host app. Like the hardware wallet will, in the case of silent payments, generate this output. It's the spend public key plus the hash of the shared secret, right? And it will send this generated silent payment output to the app. And the app would ideally want to just double check the correctness, but how does it do it? Like it cannot even compute P again, because it doesn't have the private key A, right? just cannot do it. So one step closer to it would be if you just also send the shared secret along with the public key, because then at least the host could compute the P as the hardware wallet did, right? It could compute the public key, the spend public key plus the hash of the shared secret times generator, could redo the whole computation. But the problem is the same as before. The shared secret could have some corruption, some memory bug, and then would be the wrong one, and you would be verifying really nothing at all. So how to fix this? So there's an insight, which is very important here. The insight is that the same private key of Alice is used for both her public key and also for the computation of her shared secret. It's the same public key, it's the same structure. Like one time it's times the generator, and the other times it's times the scan key. And so there is a cryptographic algorithm where you can basically prove that the same key was used in both cases without actually showing the private key at all. It's kind of like if you know signatures, like if you make a Bitcoin transaction, you sign it with a private key, and the signature is the same thing. It kind of proves you have the private key without showing the private key, right? It's a proof. And this is kind of an extension to just do the same with two sets of equations. Like you have two times the same thing, you just prove that it's the same in both cases, and there's like a specific algorithm. And this is called the discrete log equality proof. This is the technical term of it. And so armed with this, now the new flow is the hardware wallet just constructs the silent payment output. And then it also does this proof, which is a cryptographic proof that the same private key was used. And this effectively then allows, so you send everything over to the app, right? Including the new proof. And this allows the app then to verify that the correct private key was used to compute the shared secret. And then you can recompute the whole thing and verify this is all the same. And if everything checks out, the host app can be sure that nothing went wrong, like that the hardware wallet implemented the silent payment protocol correctly without any bugs or issues or anything at all. Maybe as initially, like the app, how does it know, for example, all those inputs, right? The app has the public key A of Alice, but it knows it from the transaction, right? It's in the input. It knows the generator because that's a constant for everybody. It knows the shared secret because it's been sent by the hardware wallet, including the DLEQ proof. And it knows the scan key, of course, because you pasted the address, right? It's in the address. So the app can perform all the verification. Okay, so a quick word about rollout of all of this. So Bitbox 02 hardware wallet has support for silent payments, including the app doing this correctness check as I just described, since version 445, which was released like a few days ago. So if you want to go download it, if you have a Bitbox, check it out. And we hope that with this we can like aid the adoption of this protocol, because it's kind of cool that you can just have a static address and preserve your privacy. So silent payment send support is kind of required as a first step, because no one will bother implementing receive support. Like exchanges will not bother, other wallets will not bother unless the whole ecosystem can send to it first. So this is the first step. All right, so what's next? So all of this is very new, and new Bitcoin improvement proposals need to be like defined about how you specify this proof exactly, and how you make a new PSPT unsent transaction format, which has this new generator role instead of a signing role, so that the whole ecosystem can kind of work together, right? So that if you have whatever wallet you use, like Sparrow, Electrum, Bitbox, Ledger Live, and so on, it shouldn't matter what you use. You can like interact with other pieces of the ecosystem, so everything supports it the same way. So that needs to be done. And then so this talk was more about how you send silent payments, not so much about how you receive them. But if you imagine Bob, how does he receive those coins? Basically, the naive way is he just looks at every output there is in the blockchain, just checks if it's kind of matching up with his keys. That's very inefficient, right? And there's some ways you can improve it. Like there's already some known ways where you can do it more efficiently, but it's probably still not as efficient as the traditional way. And you want just good UX. You just want to open your wallet and boom, you have all your stuff. So how do you do this? Needs more research. And then one big drawback of silent payments right now is that it only works with single signature wallets, basically. Like if you remember, Alice's key pair is based on public keys from her input, but it kind of requires that all the inputs have exactly one public key. But in Bitcoin, there's also multisig and advanced scripting and so on, but you cannot use those as inputs, right now at least. So it'd be cool to just research how you can make this compatible with more advanced scripting types and accounts and more secure accounts without actually losing your privacy. All right, that's all for today. Thank you very much. What's the microphone? Oh, here. Over
there. I read the two blog posts that you put on your website. So there's something that you developed a little bit in the blog post that you didn't quite develop here. If I understood correctly how these silent payments work to, as you say, avoid the recipient from having to scan the whole blockchain to see if he received the payment. If I understood correctly, the sender has to designate beforehand all the UTXOs that they would spend and create a shared secret based on the private keys of all those UTXOs that they might spend. Is that correct?
You don't have to pre-designate it. It's basically you just use any inputs you already have, any UTXOs you already have, like in normal traditional payments. And because they're in the transaction that you sent your coins with, this is the keys that you use in the shared secret. So it's basically embedded in the transaction itself. You don't have to let anybody know what these are because they're right there in the transaction. If I understood your question correctly.
Yeah, okay, but I thought the point was that I can send again to that same public key in the future.
Yeah.
Over several times. I send you some money now, and I send you money in a week, and in 3 weeks, and so on. So, I figured I have to choose enough UTXOs beforehand to.
You will just receive UTXOs as normal from wherever you get your Bitcoin from, right? So you accumulate UTXOs, and then you just use them in the input, and the resulting output with the shared secret will be unique if the keys in the inputs are unique. So if you use silent payments to receive, they will be unique by nature, right? Because they're already done like this. And if you have an address you reuse on the before already, then actually the silent payments protocol has a little bit more detail that I left out, where you also put in the hash of the inputs, and this makes it unique again. But I omitted this for simplicity here. Yeah.
Has this kind of always been possible, or are you kind of making use of one of the new signature schemes like Segwit or Taproot or something like this, or has it been possible with since before Segwit? It just needed to be further developed or thought of.
So the protocol kind of just specifies that the public key that you create will be embedded in a Taproot output, which is how it is defined. I think it could have been also possible before with Segwit, but it was just not done before. Yeah.
So if I understand correctly, I can have a contact list of my friends with the silent payment link, right?
Yeah.
But how do I verify that this address of my friend is not corrupted with something other?
So it works the same way as with normal Bitcoin addresses. You have to verify it some way. You maybe just call him and say please read it out loud or something. But the difference is you only have to do it once this time, because it's going to be static address, the same forever for your friend. While with the old school addresses, you have to do it every time with a new address and check that it's the right one every time. So it's kind of simplifying things. You do it one time only. Could be with your exchange, with your friends. You can put it in your contact list, verify it once, and then it's going to be good forever.
And do you have some numbers how it's already widely used, or how many wallets or hardware wallets are supporting it?
So you cannot really tell, I think, how many transactions are based on it. because no one except the sender and the recipient actually know what the transactions are, which is kind of cool. You can, of course, look at the ecosystem adoption, and so far, I think we are the only hardware wallet like Bitbox that has send support. And Blue Wallet, I think, has send support too. And on the receiving side, it's only Cake Wallet at the moment. It's basically very new, yeah. So we're at the beginning of the adoption phase. If there will be adoption, we'll see, I guess.
One more, sorry. How is it? We had paynims BIP47.
Yeah.
I don't know very deeply how BIP47 works, but why is that different from that?
Yeah, I'm also not so familiar with this BIP, but I heard that it uses it doesn't use the shared secret based on the data from the transaction, but it has some sort of a notification transaction that you have to do upfront. So if I want to send to you, I first send to you like some sort of, I don't know what this exactly is, a notification transaction, and then afterwards I can reuse your static address. So that already incurs like a more cost, right? You have to pay more fees to set this up.
Hey, I'm a UX designer, and I've been digging around in silent payments a bit. And you can add, as far as I understood, you can add on the receiving side. It's going to be pretty complex from a UX perspective because you can also have labels right on silent payment address, or you can give out different addresses for different purposes as a user theoretically. I can say I use one silent payment address for donations, one for customer invoices and whatever.
Yep.
And my wallet application, or I need to figure out which payments come from where, because I mean it's a best practice to label your transactions, at least the incoming ones, so you preserve your privacy. Is that something that you're thinking about, or is that kind of too early to really?
So that's basically all on the receiver side, right? Like if you want to receive, you have to worry about, if you want to identify payments, maybe you're a shop and you want to like say, I sold this bike to this person, so I need to track the payment. You need labels. We are not at the moment worrying about this because we don't have receive support. We only have send support. And so we will kind of wait and see how adoption goes. And if it's like a big success, then we might consider adding receive support too, and then think about all these problems. Yeah, but it's too early for us now.
Yeah, right. That's where I think from a design perspective, I also kind of said, okay, you need a way then on the hardware side and also on the application side to kind of make sense of it all if I'm a receiver of, or if I'm going to use these techniques.
Yeah.
How would you kind of view these transactions then? I mean, is it a case where block explorers need to be further developed out to be able to view the transactions, or how does it work?
So
what kind of address are you looking at? I'm a bit confused.
So the thing is, the silent payment address is never going to be in the blockchain anyway, but it's also not going to be in the block explorer. Like what you have in the block explorer is like the payment output is just going to be a new public key derived. It's going to be a taproot output. So in the block explorer, it will look like a taproot address, but it's going to be a new one for every transaction. So you cannot really correlate them because you don't know which are belonging together. So in the block explorer, you cannot paste like a silent payment address and see what. This is the whole point of the silent payments protocol, right? You cannot like just go to a block explorer and see all the transactions that go to it.
But you say it looks like a taproot receiving address.
Let's say I send
can you paste that?
Let's say you have one static silent payment address and I make three transactions for you. In the block explorer, you can find them. They will be there. They're of course in the block, but they will be 3 individual transactions, which each have a separate taproot address. But I don't know, like no one knows except for the two of us that these belong to the same silent payment address.
So that's kind of already kind of natively supported in current block explorers. So you can do that right now.
It's basically impossible. Yeah, that's the whole point of the protocol.
Yeah.
So I think it's really great to have some more privacy on the blockchain and on Bitcoin payments. Do you have a sense of when, or the timelines when, send and receive becomes more ubiquitous in the hardware, software and hardware wallet implementations? Because
I
that's
mean-
really what it's about. When does it become usable? I've never used Cake Wallet. I read about it at some point, but yeah.
Yeah, I also haven't used it before. I used it to test all of this out. Yeah, it's true. I mean, I can predict it as well as you can. I mean, it depends on user demand, I would say, and how many people are willing to put in the work. Unfortunately, implementing receive support is quite hard generally because of all the scanning problems I mentioned before. So first we have to figure out this before we can proceed. Yeah, it's tough.
So you don't have a sense, like, I thought maybe because you spent a bit more time looking into this, you might have a bit of a sense of, if we're talking months, years, decades.
I mean, it's probably going to be more like years than months. Like, I would not expect any exchange to have support for this in the next year or two. But I mean, it's hard to estimate, really. Yeah.
Okay, thanks. But kudos to get it working on the hardware wallet. That's
Thank you.
a great first step.
Okay, no, yeah. Could it be possible to still have some address reuse if someone sends Bitcoin from the same address to the same silent payment code?
Yeah, so I kind of omitted this in this presentation, but if you recall, if I go back here, like if you see the public key is the spend public key plus the hash of S, the shared secret. In reality, this is not the whole protocol. In the whole protocol, the hash is not of shared secret, but also of the input hash. It's like both together.
Okay.
And the input hash is like unique for every transaction because the UTXO is unique, right? Has a unique reference. And this way it ends up being unique anyway, even if the sender has address reuse.
Okay, now it checks out.
Yeah.
Thanks.
Good catch. Yeah. This is, by the way, also the part that the initial draft of the proposal specified the input hash as like the hash of all the inputs sorted, which is kind of impossible to do on a hardware wallet because of the memory constraints, right? The hardware wallet streams the transaction from the host step by step. You cannot really do like a reordering on the flies. I mean, you can, but it's very difficult. And so my contribution there in the review process was to just point this out and say we have to do this differently. And luckily it was like changed. So it's now basically a very quick computation for the hardware wallet to do. Okay, no more questions. Have a fantastic evening, everybody. Thanks for joining.